All right, so I don't have problems prepared like I did for the first exam or the third exam, just a set of problems that we can go over. So I've pulled up the study guide and we can go through the study guide kind of question by question, or we can get some practice wherever someone thinks or sees something they would like to practice in more detail. But I don't have those problems prepared, so we're going to have to go dig them out and find them or create them. All right, first element, past exam 3, where the limits of algorithmic computation. So first part of that was computability and decidability for Turing machines. So be able to define whether a problem is computable or decidable and use Turing machines in your answers to be able to do that. There's also this subpoint of what kinds of questions about context-free languages are undecidable. In our slides, we had some examples of what those were. Be able to justify why those are undecidable and maybe make a couple other, be able to reason, given that these are undecidable, what other classes of languages would be undecidable operations on context-free languages. We talked about the halting problem. So be able to describe the halting problem, be able to reason and understand how we show that the halting problem is undecidable. So what was that proof? How do you construct that proof? I probably won't have you redo that proof on an exam. That's too memorization focused for me, but you may need to know why it works to be able to answer a question or a similar question about another kind of problem that utilizes that same kind of ideology. If you understand how to do this, then you'll be able to describe how to do that, something like that. We talked about reductions. So know what an undecidability reduction is, be able to describe what we can show with a reduction, what is the conclusion of a reduction, and then be able to set up a reduction proof. I won't have you performing reduction proofs, but you should understand how they work, the steps of a reduction proof, be able to show, if I could go into more detail and show this proof, then I could tie this problem to this result. And here's how I would go about doing it. But then again, I won't actually have you doing it on the exam. Anything like that would take more time than I would be comfortable with for a single question. Any questions about limits of algorithmic computation? Any of these topics? Anything I can explain in more detail? All right. We had a unit on compilers. Be able to describe what a compiler is at a high level. So just a, what does it do? What do all compilers share in common? There will be some decisions that are made on a compiler by compiler basis. So just what is a compiler? Be able to describe what that is. We also talked about bytecode as one of the intermediate steps for languages to compile into. So Java compiles into bytecode. Some other languages compile into bytecode, be able to describe what bytecode is and why it's used over an assembly language or a direct translation into machine code. What does bytecode do for it? Be able to talk about the steps of the compilation process, how each of them are accomplished. So not just defining what the step is, but be able to talk about how it is done. So how is scanning or tokenizing done? How is parsing done? What are the options for how to parse? We've seen multiple algorithms for parsing at this point. You should be familiar enough to describe any of them, how they work, why they work, what their associated asymptotic notation complexity is. We talked about type checking, how to ensure your program is semantically correct. How does that work? Intermediate code generation. What is intermediate code? Why is it important? How do we generate it? Code optimization. What are some examples of code that can be optimized? Code generation. What is the end result? How do we get to that end result? So yeah, in more detail, we talked about scanning. What are tokens? Kind of like the homework question, be able to identify them, given a code example. Be able to talk about how scanning is implemented. So it uses a DFA. How does it use a DFA at an intuitive level? Why? How? Why a DFA? How can you use a DFA to recognize tokens? For parsing, we've talked a lot about it. Purpose of it tells us that a program is syntactically correct. What is the result of parsing? You get a parse tree. Be able to write a grammar or generate a parse tree for a Java-like programming language. Again, very much like your homework question on this homework. Type checking. Talked about this already. Talked about intermediate code, talked about code optimization, talked about machine code generation. We didn't talk about the symbol table and error checking. So what is the symbol table? What is stored there? When is it referred to? What kinds of errors can we determine by checking the symbol table? How do we return those errors? How do we get the information to return those errors? We talked about all of that. Parsing in general, contrast between top-down and bottom-up parsing. What do we need to show? What do we start with and what do we need to show between top-down and bottom-up parsing? Which algorithms that we talked about for parsing were top-down and which were bottom-up? What do the top-downs share in common? What do the bottom-ups share in common? Questions like that. I may give you a grammar and I may ask you to generate a top-down and bottom-up parse tree for a particular string. We have our first function. So if I give you a grammar, you should be able to calculate the first function. This can be, I'm not going to say that this is going to be the simplest possible grammars that we looked at. The grammar may or may not include lambda. So you should be able to calculate first, regardless of whether a lambda is in the grammar or not. And then be able to verify that your first function is correct to the best of our ability. Same thing with a follow function. May give you a grammar. You should be able to calculate follow. I may give you a grammar with lambda in it. Anything on either of those, on compilers or on parsing? Questions or something I can talk about in further detail? Did all that too. All right. LL parsing. What is the process for converting a context-free grammar to a non-deterministic pushdown automata using the LL parsing process? So how is that done? We also drew out the stack, state, look-ahead tuples for each of those operations. So be able to go through that process very much like we did in class. And I think there's a homework question for it that does exactly that. So be able to replicate that process on the exam. Be able to build an LLK parse table for a given grammar. I'll make this relatively short. I won't ask you to do an LL5 parse table or an LL5 table like we said in class that is way too large to throw on an exam. I can't give you a sheet of paper that's as large as this classroom, so I'm not going to try. But it may be LL1, it may be LL2. That's going to be the cap. And I would only do LL2 if it's going to be a very small grammar, something that you could reasonably put a table on a sheet of paper. Given that you have a grammar and a parse table, be able to walk through the steps of the LL1 parsing algorithm. As part of this, be able to show when there was ambiguity in your process. So when did you have to choose between a shift and a reduce? It wasn't really a reduce, that was LR, but a kind of a shift or an expansion. When you have that choice, if you're not using the LL1 table, then we had to rely on non-determinism or searching. Once we had the LL1 table, that was removed and it was deterministic. So be able to describe that difference of why and how that is deterministic. And show how the choice is removed when you have access to the table. Be able to walk through referring to the table as a way of deterministically parsing. And with all the above, be able to determine if a grammar is LLK for some K or not LLK. So be able to calculate the K if it is LLK and be able to show that it's not LLK for any K if it's not. So that's everything from LL. Then there is a little bit of cumulative content. These are the only kinds of questions that I will ask you about content from the entire class. I'm not going to pull out a question that I could have reasonably asked you on exam 1 or exam 2 or exam 3. So you do not need to go back and memorize or completely re-understand the details of concepts that were covered on prior exams. The only kinds of questions I will ask are high-level questions. Things like a more specific version of you should know at an intuitive level how everything we've discussed so far ties together. So how do different state machines relate to different language classes? I won't ask you to explain or draw a DFA or draw an NPDA as part of this, but I might ask you about what do the different classes of languages that we have talked about mean? Why do we care to study these different language classes? What can they do for us? For grammars, why do we represent programming language syntax with grammars? Be those regular grammars or context-free grammars or context-sensitive grammars. I'm not going to have you solve a problem with one of those, but be aware at a high level of what a grammar is, why we use them in computer science theory. Then things like, how do we determine a language's language class? If we have a language, what process would allow us to determine whether it is regular or context-free or recursively enumerable or non-recursively enumerable, or some subset of those? So just how would we do that? Let's say I give you a language and it happens to be recursive. How would we show that it belongs to the class of languages that is recursive, but not a more specific class of language than that? We need 2 steps. What are those 2 steps? We need 1 to show that it's recursive. We need to construct a Turing machine that shows that it's recursive. So we need the generator and verifier from before. We'd also need to show that it's not context-free via the context-free pumping law. I'm not going to have you do either of those things. I'm not going to have you say what a construction would look like. To be aware that those are the couple of steps that you would need to show that a language belongs to that class. That's an important takeaway from the class as a whole, is there is a process to show that something is recursive or smaller, and there's something to show that it is not context-free, it's larger than that. And the combination of a less than or equal to and a greater than will hone in on the band of Chomsky's hierarchy that is just recursive. Yeah.
It's recursive and not.
And not context-free. So it's recursive, but it's not more specific than recursive. So it gets you just that band of the Chomsky hierarchy. And again, that's a very high level. I will not ask you details about that process. Another high level question, how do state machines help us model a language's membership? Every state machine that we looked at this quarter was a membership kind of question, or could answer membership types of questions. So why do we use state machines, and how does the construction of a state machine in general allow us to model a regular language or a context-free language or a recursive language? Why do we use them for that? Similarly, how do we use grammars to model a language's membership? kind of what are the ties between using state machines and using grammars? Because frequently throughout this class, we were converting between a grammar-based representation and a state machine-based representation of the same idea. Why are these two things studied or used? Why not just use one or the other? Why do we care about grammars? Why do we care about state machines? Why do we study both of them together? What kinds of interesting membership questions are there in computer science? Why do we care whether a language is regular? Why do we care whether a language is context-free? Why do we care whether a language is recursive? So I already talked about number 5, how are automata, I'm thinking automata and grammars, but automata and compilers, how are they linked? Where do we use automata in the compiling process? And for what? That's partially part of what's above, where DFAs are part of the tokenizing process and non-deterministic pushdown automata or context-free grammars are used as part of the parsing process. Then at a high level, why do we study the theory of computation? So questions around computability and decidability. Why was that worth studying? What kinds of questions could we answer by studying that? What does it reveal about computer science as a field? So a lot of what you study in other classes than this is a very specific, how do you do something? And in this class, the theory of computation part is it possible to do something? Given infinite resource, which seems like it doesn't have quite as much of a tie to the everyday. So why did we talk about it? Why did we study it? What can we take away from this class with respect to the theory part of it? So I may ask any questions that target any of these ideas or subcategories of these ideas. But you can prepare yourself to be able to answer that question by just thinking about and reflecting on the class as a whole and how it related to some of these questions. Any questions on any of the cumulative content or the kinds of questions that might be asked with regards to cumulative content? So this is not a cumulative exam, but there will be some questions that target some of these kinds of broad scope questions. Nothing? No questions? I don't know if that's good or bad. That either means I could take the exam today. I'm fine. I feel confident. Or it could be, I just need some time to digest this and I'll figure out the questions as I look into this in more detail. Or wait, we covered all of this? Anywhere in between. So I guess maybe the best follow-up question would be, what do we feel least prepared for, weakest at, could use some extra practice with?
I would like more practice on the side of the questions about context-free languages.
Okay. I can also spend some time this afternoon preparing some questions for tomorrow. So if I can at least identify what kinds of topics we want to cover with respect to that, I can work on that. So context-free undecidability.
I think it's just because I haven't gotten to it yet, but the converting the LL parse into an NPDA represent that process.
Yeah,
I guess that maybe if it would be something on the exam, would be something that's probably beneficial to go over.
sure.
You know.
Say it for probably the freaking chart again.
The LO parse table. Okay.
but also like computability inside of it.
Okay.
Just overall. I should call that.
So, other medication, like production group.
Yeah, so it sounds like a lot of this first section. It is the most abstract section of the entire class, for sure. So I think we can target some of this with either going back through some of our in-class examples as a refresher as to how, and then maybe we can follow that up tomorrow with some new problems. Maybe that would be the best way to target the rest of today. Does that seem useful if we go back through some of those and re-explain them so that hopefully using some of the context that you've acquired since we went over it the first time, we can see more of why and how? Yeah, we can absolutely do that. Get there from Williams. All right, based on what's here, without using this wording, maybe to help, this can help ground you. What was the difference between computability and decidability?
Computability means there's a function that exists that allows us.
Yeah, so you're going to have a domain and a range, and computability is going to create a function between the domain and the range. So the output to this can be arbitrary. It doesn't have to just be yes or no. It's not a binary output. Decidability is a binary output. The answer is either yes or no. And we use that for the membership question. For languages, is this string in this language? The answer is either yes or no. So that's why that is the decidability question. It's also the decidability question in math. But something that is computable may require a function as what converts the input into the output. So both of these are kind of the class of recursive languages. Recursive can answer yes and no, but recursive also basically could contain something that is computable. But it could also, so something that is computable will tell us the output if the output exists, but can also tell us that no such output exists if it is uncomputable. If that particular input does not have an associated output, it would be able to tell us that. How did we define the halting problem? How did we set up and prove the halting problem? Anyone want to take a stab at explaining that?
Yes. We first assume there's a halting or a Turing machine, we'll call it H. And that Turing machine always tells us whether something halts or if it doesn't.
Yeah, so this is a proof by contradiction. We're
Yeah.
going to assume that we can solve the halting problem. There is such a Turing machine that solves the halting problem. There it is.
Right. So then we create another Turing machine T. And we basically pass an H into T. And by doing that, I don't think I'll be able to explain it word for word, but basically we're showing that when we pass an H contradicts itself. And in turn says that it halts when it doesn't halt and it goes into
Yeah.
Oh, sorry, T says the opposite.
We attached something to H. What were the components, kind of the Lego extenders that we attached to H to make it do that opposite thing?
We add another transition, right? we do that to T though, right?
Yeah, so basically we're turning H into H plus, or whatever we want to call it. The video called it H plus.
Uh-huh.
Where we extend, if the answer is yes, it halts. Then we're going to attach something that forces it to go into an infinite loop. So if H says it halts, then H plus immediately takes as input that yes, it halts and goes into an infinite loop.
Yeah.
And on the other hand, when H tells us no, this program does not halt, then it immediately halts and tells us that the program halts. Sorry, doesn't halt.
Yeah, so that's the same thing, I guess, what I was saying, but I watched a different video and it was really interesting because they drew a little. They basically represented the Turing machines as squares, and
Yeah.
for H plus, instead of the way we did it in class where they just did those transitions, they kind of made it so like the larger H plus was like eating H. And so it was a little bit different, but yeah.
Yeah. Then we feed H plus its own source code as both machine and string. And the question is, does H plus halt on its own input, on itself? And we get a contradiction because if H plus halts on itself, then by definition, it must go into an infinite loop. So we should be able to determine that it halts from this. The halting problem says that H tells us this, that it halts. But now we've constructed a machine where when the answer is yes, it halts, it goes into an infinite loop. And when the machine doesn't halt, then it halts and tells us that it didn't halt. But the whole purpose of this was that we could show that. So yes, we derive the contradiction from there, that using the machine that solves the halting problem, we can get the exact opposite response than we expect. And there's no way to determine that it halts, since it goes into an infinite loop. It's ambiguous as to whether it is in that infinite loop or whether it will eventually halt and tell us no, that it doesn't halt. The only way that it halts is if it tells us that it will never halt. But if it never halts, then it wouldn't stop and tell us that. Contradiction.
I do feel like the easiest way to see this is through like a picture.
Yeah.
Because when you talk about it, I don't know, for me, it's always visualizing that.
Yeah. That's why I have the video. I originally was just showing that one clip of that larger video as just here's a visual of that idea. But then I just found, you know what, we have the time for the entire video and it's super interesting and relates and ties to everything that we've talked about. So I show the whole thing when I can get sound in this room. So yes, that was the halting problem. What else did we have questions on? We had LL parse tables. So in computability and decidability, we have reductions, but people didn't specifically ask about reductions. There were the undecidable problems for context-free languages. We can talk about that. So in class, we just mentioned on this slide, we could find that using reductions, we could prove the different classes of languages were undecidable with regards to operations on context-free languages. Here were some of the results. These are all reduction proofs, and we could use the post-correspondence problem as a middle ground, as an undecidable problem. But a lot of these either reduce to post-correspondence or reduce to the halting problem directly. But we have this entire class of undecidable languages where if we could decide any one of them, then we could decide all of them. But they relate to each other in ways that say, if this is decidable, then that is decidable. And that is something that we've already shown to be undecidable. The only proof that we directly have that something is undecidable is the halting problem. And basically all of these collapse into the halting problem in some sequence of steps. To say, if we could solve this, then we could solve that, then we could solve the other thing, and then we could solve the halting problem. So a lot of this theory relies on that halting problem proof indirectly. It's worth spending a little bit of time as you prepare for this, probably sitting down and thinking about just pick one of these and try to make it work. It's like how could we decide this? Come up with the intuition for why this problem is undecidable. I think I tried to talk about a few of these in class, but let's pick one and do it now. Which one of these options is least intuitive to you? And you'd like some intuition for why wouldn't we be able to decide this?
To G1 and G2 are context-free grammars is L G1 a proper subset, right?
Is this a subset?
Or just
Yeah, proper subset would be without the bottom
Without.
bar. So the second one. So basically we're trying to determine both is every string in the first grammar in the second grammar, and is there a single string that is in the second grammar that is not in the first grammar. That would be a proper subset. All we need to do to show that it is a subset is to be able to prove that every string in grammar 1 is in grammar 2. That's all we have to prove. How would we go about doing that? So with a context-free, we're going to pass, we have kind of a generator. With that generator, we could look at, and with our knowledge of theory of computation, we could come up with an enumeration that would get every string eventually in the star closure of the alphabet of grammar 1. We would then have to pass all of those through that grammar and have it be able to tell us, yes, it's in grammar 1, or no, it's not in grammar 1. Then we would also have to pass that through grammar 2. To be able to answer yes to this, we would have to go through an infinite number of strings, because both of these languages are infinite. There are an infinite number of strings in grammar 1, there are an infinite number of strings in grammar 2. You can imagine that we are 10,000 years into this process. We have found millions, billions, trillions of strings in grammar 1, and for every single one of those strings, we have verified that it is in grammar 2. Can we conclude that the language of grammar 1 is a subset of the language of grammar 2? It's not a proof. We may have some pretty overwhelming evidence, but there may be a string. And in fact, I could come up with a grammar that if you tell me I have parsed 1 trillion strings in this enumeration order, I could come up with a grammar where somewhere past 1 trillion strings, there is a difference. But it looks identical for those first trillion, given the enumeration procedure that you give me. So because of that, it would be ambiguous, regardless of how many strings you've processed, as to whether the language of grammar 2 is all contained within, language of grammar 1 is all contained within the language of grammar 2, or whether we will eventually find a difference. We know and can answer immediately when we find any string in grammar 1 that's not in grammar 2. We pass it through grammar 2 and the answer is no, it's not in grammar 2. We can conclude immediately and say, these are distinct. But in order for this to be recursively enumerable, then we need to be able to answer yes. And we can't answer yes. We can only answer no. Questions on that? How much sense does that make? Do we agree with me that that's a reasonable conclusion from that? Answering yes is impossible. We can get more and more evidence that the answer is likely to be yes, but we will never have a proof that the answer is yes. If the answer is no, we can prove it in a finite amount of time, but it's a scalable amount of finite time. We don't know if we've reached that finite amount of time yet or not, if there is a difference. You can apply similar kinds of logic to all of these problems, and it's worth just thinking about if I gave you something like this. This is something that I could throw on an exam. Something like, if G1 and G2 are context-free grammars, is the language of G1 a subset of the language of G2? And you could walk through, if this is undecidable, how would you show it? You would say you'd reduce it to a known undecidable problem, but intuitively, it is likely to be able to be done because here is why you can't answer yes. Here's how you would be able to answer no, but at any particular point in time, it's ambiguous between whether the answer is yes or whether the answer is no, and we just haven't found the contradiction, the counterexample yet. You're searching for that counterexample, but since both languages are infinite, you never know if you just haven't gotten to the contradiction, to the counterexample yet. Sorry, I should not mix those words up. You haven't gotten to the counterexample yet.
For number 3, if it's a context-free grammar, it's LG1 regular. I mean, my immediate thought would be that we would do a context-free pumping lemma.
A regular pumping lemma?
Wait, is it a context-free grammar? Oh,
So that's how you'd answer no, it's not regular. But how would you answer yes, that it is regular?
oh, I see.
We need an algorithm to produce the DFA. And you'd be able to answer yes if you could create the DFA, but is there an algorithm that takes in a context-free grammar and can either go through the regular pumping lemma to answer no, but the answer is going to be answered. The question is going to be answered yes. And that becomes the challenge of there's no enumeration procedure for creating every possible DFA. So you couldn't try to create every possible DFA and see if that DFA matches that language.
So in this case, it means a context-free grammar that may or may not also be regular.
Yeah. So answering yes, then it is regular. You could answer no, it's not regular with the regular pumping lemma. But answering yes is always going to be ambiguous. Given that we haven't found the DFA for it yet, does the DFA exist? Other questions on this? Or anything else from this section, at least without further preparation of questions or examples?
The same idea of not being able to answer yes is applied to all of these.
Yeah, in order to be undecidable, we can't answer yes. We may be able to answer no, but we for sure cannot answer yes. That is what it means to be undecidable. There is no enumeration procedure. It will be ambiguous between whether the answer is yes or whether the answer is no, and we just haven't found the counterexample yet, or found the example yet. Next, I think we were in LL. We had questions on parsing using this process. So what were the rules that allowed us to create an NPDA based off of a context-free grammar modeling the LL parsing process? What are the two classes of rules that we have here? There's one class along the top and one class of the transitions along the bottom.
Isn't this basically the shifting versus expanding?
Yeah. Yep. So along the bottom, we're reading a character from the input and we're popping that character off the stack as a way of matching. This is the last character that we generated. That's the first character that is going to be expected to be matched in the string. There's the match. We can move past that character and delete that character from the stack. We can also, when we see non-terminals, expand those non-terminals with the goal of producing the first character that we need to match. So to do that expansion, we don't read any characters in the string, but we replace a left-hand side with a right-hand side, a left-hand side with a right-hand side, given some production that's in the grammar. And then we just have the initial transition that puts the start non-terminal on the stack, which is, since this is a top-down procedure, that makes sense. You start with the start non-terminal, you end with the string. And once the stack is empty, that says that we've parsed everything. We converted that S into a string and matched it to all of the characters that were in the string. There's nothing left in the stack. And once we reach that point, then we got rid of the S. We just have to make sure that we also move past the exact appropriate sequence of symbols that we saw in the string. So the example that we used was ABCAB and that grammar. So this was the initial transition going from Q0 to Q1, pushing S onto the stack. Then we expanded the S into ASB. We could then read and map this A to the expected A that was the first A in the string. There it is. So we get rid of that. We move past that character. Our look ahead is now a B. So we're now trying to produce a B as the top character on the stack. So to do that, we had to convert the S into an A via that transition rule, where we could immediately replace an S with an A, and then replace the A with a BAA. That allows us to map the B. This is the process that allows that B to be up front. We can move past it with an A on top. We now need to map to a C. There was a transition that allowed us to replace the A directly with a C. Then all that's left is the C and the A and the B that are the C, the A, and the B in the string, where we could end up with the stack being empty. The look ahead is the end of string character, because we got past every single character in the string, and we end up in a final state. We can transition to there because of that. What was the problem that we had at this point? We hadn't introduced something yet.
Non-determinism.
Yeah, we needed non-determinism. Where was that non-determinism present?
In the production, like the production expansion.
Yeah, whenever we have a non-terminal, we don't know which non-terminal to apply. There's S arrow ASB and S arrow A. There was a different reality where we produced this S became an A directly. We did not do that. Same thing here. When this S became that A, there was a separate reality where there was a B, but this S became an ASB. We chose not to do that. This A could have become a C. This A could have become BAA. So those are all of the places that we chose to do something. But note that when this A is on top of the stack, this also would have had two branches. So there's a lot that we chose not to do or didn't search through. This just defines the correct procedure, not every possible procedure. How did we remove that ambiguity? What did we do that allowed us to know that this was the correct path to take?
Look at it.
Yeah, we needed to look ahead. Well, we have the look ahead here, but what did we use the look ahead to do?
Loaded more character then.
Potentially, we only needed a single look ahead here, but we built a data structure. We built our LL1 parse table. So we calculated first and follow. And then from there, we built the LL1 parse table. And with the LL1 parse table, that allowed us to say, when we have this look ahead is an A, and there is an S on top of the stack, the LL1 parse table said that the way to do that was via expanding that S into this. This S to A was not in the LL1 parse table. So with a lookup to that, we knew to apply this rule and not that rule. Here, when we have an S and a look ahead of a B, this is where it said S to A. So with a lookup, we knew to apply this because of the LL1 parse table. We knew not to do this. Same thing here. You'd look at row A, column C, and that told us to do this, not that. So we didn't have to do any searching because of the LL1 parse table. And that was possible because this grammar was LL1. If this grammar had been LL2 or LL3, then we could not have used an LL1 parse table. We would have needed to use an LL2 or an LL3 parse table. If it weren't LLK for any K, we wouldn't have been able to build such a table that allows us to know for sure that it's this and not that. We'd either have to search, we'd have to do something intelligent, but brute force searching, as we discovered earlier in the quarter, is exponential in complexity. And CYK was an intelligent search through this, but it was cubic. So if we don't have access to removing this non-determinism, we're picking between an exponential complexity solution and a cubic complexity solution. Neither of which are anywhere near as good as pre-processing this, coming up with the table, and then being able to, in real time, just refer to the table and know at each one of these steps which production to take. That removes the need to search completely from this process. But if you needed to identify where is the non-determinism, how did we know to remove that non-determinism, to get rid of it? It's embedded right here at the steps where there's a non-terminal as a process, as the top of the stack. That means that there are multiple possible productions, and the look ahead tells us which production to apply from this if we look at the LL1 parse table, because that pre-processing removes the need to search. All right, I can come up with some extra examples of this so that we can make sure that we can do this process. We'll do that tomorrow, and we will also produce LL1 tables. So a little bit of first and follow and an LL1 table. Do that tomorrow. That probably will take out fast, and I'll probably have some time to answer further questions that you find between today and tomorrow, and or be able to answer some questions on your projects. Homework due tonight. The TA did say he's a little open and welcome to any delays on that. So if you need to get this in over the next couple of days, that's okay. Just don't expect it back before the final, if that's the case. So get it in, yeah, get the homework in by tonight if you want to be sure that it's returned to you by the time you take the final. He's going to be working on that tomorrow. But if you need a little bit more time for that, he has a little bit of so busy that he can space that out into the next little bit, and that won't be a huge bother. So if you need the extra time, feel free to request it, but not if you'd like to use the result from that and the feedback from that as part of your preparation for the final.
When are you getting our 3 grand package?
He's grading it today. So I may also be able to return that to you tomorrow.
Yeah, that's all right, guys, you get.
According to him, every time Josh asks him about it, he puts on a 1 hour timer where he does not think about the exam.
I already know I got the gold medal this time, so. We're fine.